Hello again. Welcome to the third module. In the previous module, we discussed 4 design principles useful in object-oriented modeling and programming: abstraction, encapsulation, decomposition, and generalization. You also saw how to express your object-oriented model using a UML class diagram and in Java code. The class diagram is great to capture the structure of the problem and the technical design of its software solution. In this module, you'll see general guidelines when evaluating the structure of your software solution so that it's flexible, reusable, and maintainable. As well, we'll talk about modeling behaviors of the objects in your software using the UML state and UML sequence diagrams. Let's jump right in. Here, you are going to learn about evaluating design complexity. The average person can only hold 7 things in short-term memory. This was observed in a psychology paper by George Miller, in which subjects had to recall 1 to 14 random sounds and images. Subjects started to fail at recall when the number reached around 7. When you are programming, keeping modules simple is critical. Once your design complexity exceeds what developers can mentally handle, bugs will occur more often. So you must have a way of evaluating your design complexity. Since design complexity applies to both classes and the methods within them, we will use the term module to refer to any sort of program unit like these. The metrics you will use to evaluate design complexity are coupling and cohesion. Coupling focuses on complexity between a module and other modules. Cohesion focuses on complexity within a module. These 2 ideas will help you to better apply object-oriented design principles and achieve a more manageable system. When you design your system, you combine various modules together. Think of a bad design like puzzle pieces, where your modules are the pieces. You can only connect a puzzle piece to another specific puzzle piece and nothing else. On the other hand, let's think of a well-designed system like Lego blocks. You can connect any 2 Lego blocks without much trouble, and all Lego blocks are compatible with one another. When designing your system, you want to make it like Lego. That way you can easily connect and reuse modules together. Coupling for a module captures the complexity of connecting the module to other modules. If your module is highly reliant on other modules, you would say this module is tightly coupled to others. This is like having puzzle pieces. On the other hand, if your module finds it easy to connect to other modules, this module is loosely coupled to others. This is like Lego. You want coupling for your module to be loose or low, not tight. When evaluating the coupling of a module, you need to consider degree, ease, and flexibility. Degree is the number of connections between the module and others. With coupling, you want to keep the degree small. For instance, if the module needed to connect to other modules through a few parameters or narrow interfaces, then the degree would be small, and coupling would be loose. Ease is how obvious are the connections between the module and others. With coupling, you want the connections to be easy to make without needing to understand the implementations of the other modules. Flexibility is how interchangeable the other modules are for this module. With coupling, you want the other modules easily replaceable for something better in the future. Again, like Lego. Coupling only concerns complexity between a module and other modules, but you also need to consider complexity within the module. That's where you would look at cohesion. Cohesion represents the clarity of the responsibilities of a module. If your module performs one task and nothing else, or has a clear purpose, your module has high cohesion. On the other hand, if your module tries to encapsulate more than one purpose, or has an unclear purpose, your module has low cohesion. You want high cohesion. If you find your module having more than one responsibility, it is probably time to split your module. Let's now look at a more detailed example of coupling and cohesion. Suppose we have a class called sensor that has 2 purposes, getting humidity and getting temperature sensor readings. Here we have a get method that takes a 0 flag if you want it to return the humidity value, and takes a 1 flag if you want it to return the temperature value. Now let's evaluate this sensor class based on coupling and cohesion metrics. Since this sensor class doesn't have a clear single purpose, it suffers from low cohesion. Look at this get method. Is it easy to determine what is happening? Since it is unclear what control flag means, we would have to read inside the method itself in order to know what values to give it. This is not respecting encapsulation, which also shows our method is unclear and lacks ease. This lack of ease makes get method harder to use, and in turn makes any caller tightly coupled to it. Let's look at a new design of the same system. The sensor class is now replaced with a humidity sensor class and a temperature sensor class. Each of these classes has one clearly defined purpose. Since each has a clear purpose, you can say that these classes are highly cohesive. The get method is now not hiding any information like before. We don't have to break encapsulation to look inside the method. You could reasonably assume that humidity sensor's get method returns humidity, and temperature sensor's get method returns temperature. This makes another module that uses either be loosely coupled. In general, there's a balance to be made between low coupling and high cohesion in your designs. For a complex system, the complexity can be distributed to between the modules or within the modules. As modules are simplified to achieve high cohesion, they may need to depend more on other modules, thus increasing coupling. As connections between modules are simplified to achieve low coupling, the modules may need to take on more responsibilities, thus lowering cohesion. You now have the skills to evaluate your system's design complexity using coupling and cohesion. However, being able to evaluate design complexity is just the beginning. To really solidify your knowledge of coupling and cohesion, you're going to need to start applying good design to your system so that they have low coupling and high cohesion.